G'day guys, we're going to do some more proofs, and this time we're going to use some circle concepts. Alright, so the first question here is O is the centre of the circle as shown. OX bisects BOC, so that's given in the diagram there. Prove that BOX and OAC are in fact equal, those two angles. Alright, so probably lots of ways of doing this. I think I'm going to show you, I reckon the easiest way for me is to do that. Now when you're doing these things, sometimes you need to draw some different diagrams that may help you when you're actually doing it. Alright, so the thing I'm going to picture here is that we have a isosceles triangle there. Alright, so if we were doing that, then this angle there is in fact 2 dots. Okay, this angle here we're going to call alpha, and we're going to call alpha. Alright, so now we've got this triangle here which is we've just labelled it. Now if we know the sum of the internal angles is equal to the external angles, so that's going to be 2 alpha there. Alright, then the other thing we know about this triangle is that's a semicircle, so we know that angle there is 90 degrees, don't we? Alright, so we know that angle there is 90 degrees. So therefore, if that's 90 degrees, now think about this middle line. The middle line there, we have a line going something like this. We have 2 dots, we have 2 alpha on the other side. Well, it's actually the other way around. But we know that 2 alpha plus 2 dots is equal to 180 degrees. So therefore, alpha plus a dot has to be equal to 90 degrees. So if I'm thinking of this triangle here, the big triangle that I've got, this big triangle that I've got here, I've got 90 degrees there, I've got alpha there, so therefore that must be a dot. Got the idea? So that I've actually proven that that there is in fact going to be the angle dot. So when we're doing proofs again, it's about working out what you want to do first of all with that, and then actually writing down what you've got. Alright, so I've drawn my triangle. So sometimes drawing an extra triangle in here will actually help you with your explanation. So I've got 2 dots. I'm going to say alpha, 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 and so therefore that is O, C, B. So we'll say let angle OBC equal angle OCB equal alpha. We know it's an isosceles triangle as OB equals OC isos triangle. Okay. Then we know in the middle that we've got angle AOC equals 2 alpha. That's the external angle. Sum of internal angles. Right, so that's what we know there. And so therefore, we know that 2 alpha plus 2 dots equals 180 degrees. Angle AOB. So therefore alpha plus beta, alpha plus dot I should say, alpha plus dot equals 90 degrees. Right, and so therefore angle OAC has to be equal to alpha, and that's to 180 degrees in triangle. Right, so we've actually proven that the angle there and this so on has to be the same angle. Now the second part of this is actually a bit trivial now. OX is parallel to AC. Right? So if those two things are parallel, they have to be, because they are what we call corresponding angles. So I'm not going to write that down, but that's what you need to sort of talk about, those being corresponding angles. And then the concept of an isosceles triangle. We've proven that OBC is in fact an isosceles triangle, and so therefore for that to be an isosceles triangle, we know that that has to bisect, OX has to bisect the line BC, which means it has to be, those two lengths have to be the same, which means it has to be 90 degrees with that. Alright, so that's the end of that proof there. Let's do this one over here where we've got this diagram given to us, and again we have to think of a strategy of how we're going to solve this problem. Alright, so AB is diameter of a circle, so we know obviously we've been given some things like that we know is that length there, we know that's also that length there. Right, so what we could do is call that alpha, and then that would mean that's alpha, wouldn't it? And then we could say that this angle here is an external angle, so that would be 2 alpha. Right, that angle there, wouldn't it? You know, that would work. Or maybe what we should do is start with these angles in here. That's what we'll do. And it'll be easier to do it on the big diagram. Right, so here's my thinking. We'll call this angle here alpha, that angle there alpha. Right, so if that's the case, then we know that this angle, the external angle over here, is 2 alpha, which means that this angle in here has to be 180. Take 2 alpha. That angle there we know is 2 alpha as well, because that's an isosceles triangle, isn't it? Right, that's what we're using with these things here, isosceles triangles. Now, if we're thinking about this whole angle here, that angle there has to be the sum of those two, which means that that whole angle there has to be 4 alpha. Okay, and if this one's alpha, then this angle here has to be 3 alpha. Right, so that's our thinking with that logic there to find that. Now that will then prove that this angle is 3 times this angle here. Alright, so that's our logic about how we're going to do there. So again, when we go to do these things, we have to tell the thing that we're going to make it, you know, we've got to set it up as a proof. Right, so let angle x o y equal angle o y x equal alpha. Right, now we know that's an isosceles triangle, so that's okay. So we're using that proof. Then angle, now I don't even think we even need to know that 180 take there. And we need to know that angle OXA equals 2 alpha, and that's the external angle, equals sum of internal angles. Right, and so if we know that, then we know that OX equals OA, and they are radii of a circle, and so therefore angle OAX is equal to 2 alpha. So therefore, so that's an isosceles triangle again. Then angle XOB has to be equal to 4 alpha, and that's external angle equals sum of internal angle. And then, so therefore, then we can say that angle YOB is equal to 4 alpha, take alpha, which is equal to 3 alpha. Alright, so therefore, angle YOB is equal to 3 times the angle of YOX, and we've proven what we need to prove. Alright, so again using the same sort of things over there. Now the next question is actually not giving you a diagram. Okay, so you've actually got to draw your diagram. So essentially we've got a circle here, dodgy circle, we've got our diameter there AB, just put O in the middle, that's what we always do. We've got CD, which is a chord which is parallel. So CD is a chord, so C and D, and that's parallel, so therefore we can put a little line on it showing them the parallel, a little arrow. Prove that BC bisects angle DCI regardless of where CD is. Alright, so if you're going to do that, then we'll just draw that line in. So that line there is COCD. Right, and then we have to show that BC bisects it. So we have to try and show that this line bisects it there. Alright, so that's what we have to try and do in terms of that. Now, what I'm thinking of is we could say something like CO equals OB, and they are radii of circle. So that's true. So if they, therefore that angle there is called alpha, and alpha. So we say let angles OCB equal angle OBC equal alpha. Right, and that's due to the fact that they're isosceles triangles. And then what we could say is, we're being told that BC, we know that CD is parallel to AB, therefore angle DCB has to be equal to alpha, because they are a Z angle or alternate angle. So it's an alternate angle. So therefore B bisects DCO. Okay, so therefore we've done that proof as well. So it's just a matter of working through. Again, I think the strategy is think about what you want to, how you want to do it first of all before you start actually writing out how you're going to do it. These can be a bit tricky, but you get your head around it and you can get them done quite simply after a little while.